Dark matter, the invisible universe, a scientific narrative based on observed physics. The first clue: something is missing. The universe does not reveal its structure easily. It must be measured, calculated, and inferred through indirect evidence. In the early 20th century, astronomers began to realize that something fundamental was wrong with their understanding of cosmic mass. The first major indication came from the motion of galaxy clusters. When Fritz Zwicky studied the Coma cluster, he applied established physical laws to determine whether the cluster was gravitationally stable. The expectation was simple: the visible mass inside the cluster should be enough to explain the motion of its galaxies. It was not. The galaxies were moving too fast. According to the calculated mass, the cluster should have broken apart long ago. The gravitational force produced by visible matter was insufficient to keep it bound, but the cluster remained intact. This contradiction implied the presence of additional, unseen mass. Zwicky proposed that this missing component existed, but did not emit light or interact with electromagnetic radiation. He referred to it as dark matter. At the time, this idea was controversial and largely dismissed due to limited observational data. However, the discrepancy did not disappear with better instruments. It became more pronounced. Galaxies that defy gravity. By the 1970s, more precise measurements of galactic motion were possible. Vera Rubin and her collaborators began studying spiral galaxies in detail, measuring the rotational velocities of stars at different distances from galactic centers. According to Newtonian physics, rotational velocity should decrease with distance from the center of mass. This principle is observed in planetary systems, where outer planets move more slowly than inner ones. Galaxies, however, did not follow this rule. Instead, their rotation curves remained flat. Stars at the outer edges of galaxies were moving at nearly the same speed as those near the center. This result was unexpected and physically inconsistent with the amount of visible matter. If only observable mass existed, the outer stars should not have remained gravitationally bound. Their velocity should have allowed them to escape into intergalactic space. They did not escape. They remained in stable orbits. This indicated that galaxies contained far more mass than could be observed. The missing mass was not located in visible structures such as stars, gas, or dust. Instead, it appeared to form an extended, invisible halo surrounding each galaxy, the invisible framework of the universe. As observational astronomy advanced, additional lines of evidence confirmed the same conclusion. Gravitational lensing, where light from distant objects is bent by massive structures, revealed distortions far greater than could be explained by visible matter alone. Galaxy clusters exhibited gravitational effects that required significantly more mass than was directly detectable. Large-scale cosmological surveys also showed that the universe's structure could not be reproduced without introducing an unseen mass component. Modern simulations of cosmic evolution demonstrate that without this additional mass, galaxies would not form as observed. The large-scale filamentary structure of the universe would not emerge. This invisible component is now known as dark matter. It does not emit light. It does not absorb light. It does not interact with electromagnetic forces in any measurable way. Yet it exerts gravity, and that gravity shapes the universe at every scale. Current cosmological models estimate that ordinary matter accounts for only a small fraction of the total mass energy content of the universe. The majority remains invisible and undetected, except through gravitational influence. The structure behind everything, dark matter, is not distributed randomly. It forms a vast, interconnected network known as the cosmic web. Within this structure, galaxies are not isolated objects, but form along dense filaments of invisible mass. Between these filaments are enormous voids where very little matter exists. This structure is not the result of visible matter alone. It is shaped primarily by dark matter, which acts as a gravitational scaffold for galaxy formation. Without it, the universe would look completely different. Galaxies would be fewer, less stable, and more randomly distributed. Large-scale structure would not have formed in the way it is observed today. In essence, the visible universe depends on something that cannot be seen. The search for direct evidence. Despite overwhelming indirect evidence, dark matter has never been directly detected. To solve this, physicists have built extremely sensitive detectors in underground laboratories, shielded from cosmic radiation and environmental interference. These detectors are designed to capture rare interactions between hypothetical dark matter particles and ordinary atomic nuclei. At the same time, particle accelerators attempt to recreate conditions similar to those moments after the Big Bang, where dark matter particles might be produced and detected indirectly through missing energy signatures. However, after decades of experiments, no confirmed detection has been achieved. Only gravitational effects continue to confirm its existence. Why dark matter remains unseen. The absence of direct detection is one of the most important aspects of the dark matter problem. Despite decades of increasingly sensitive experiments, no confirmed interaction between dark matter and ordinary matter has been observed in a laboratory setting. This does not mean the evidence for dark matter is weak. On the contrary, its gravitational effects are consistently observed across multiple independent systems. Galaxies, galaxy clusters, gravitational lensing, and the large-scale structure of the universe. The challenge lies in its apparent non-interaction with electromagnetic force and its extremely weak coupling with known particles. In other words, dark matter does not behave like anything currently described in the standard model of particle physics. The particle hypothesis. One of the leading explanations is that dark matter consists of unknown particles. Among the most studied candidates are weakly interacting massive particles, or WIMP. These hypothetical particles would have mass and would interact through gravity and possibly the weak nuclear force, but not through electromagnetism. This would explain why they do not emit or absorb light, making them invisible to telescopes. If WIMP exists, they would pass through ordinary matter constantly. Trillions of them could pass through a human body every second without any measurable effect. Only in extremely rare cases might one interact with a nucleus in a detectable way. This is the principle behind direct detection experiments. Yet despite extensive searches, no confirmed WIMP signal has been found. Actions and alternative candidates. Another proposed candidate is the action, a hypothetical particle originally introduced to solve a different problem in particle physics related to the strong nuclear force. If actions exist, they would be extremely light and interact very weakly with matter. Under certain conditions, they might convert into photons in the presence of strong magnetic fields. This has led to specialized experiments designed to detect such conversion. However, like WIMP, actions remain undetected. Other exotic possibilities have also been proposed, including sterile neutrinos and other particles beyond the standard model. None have yet been confirmed. Gravity under question. While particle-based explanations dominate mainstream research, another approach challenges a deeper assumption, that gravity behaves exactly as described by general relativity at all cosmic scales. One alternative class of theories modifies gravitational laws rather than introducing new matter. Among these is MEN, or modified Newtonian dynamics, which suggests that Newton's laws may behave differently at extremely low acceleration, such as those found at the edges of galaxies. MEN can explain certain galactic rotation curves without requiring dark matter. However, it struggles to explain galaxy clusters and large-scale cosmological observations as effectively as dark matter models. For this reason, most cosmological evidence still favors the existence of an additional unseen mass component, rather than a modification of gravity alone. The standard cosmological model, the current leading framework in cosmology, is known as the lambdictum model, which stands for lambda-cold dark matter. In this model, the universe consists of ordinary baryonic matter, dark matter, and dark energy. Dark matter plays a crucial role in structure formation. It provides the gravitational framework necessary for galaxies and clusters to form over billions of years. Without it, simulations of the early universe fail to produce the observed distribution of matter when dark matter is included. However, the large-scale structure of the universe closely matches observations from telescopes and cosmic survey. This agreement between simulation and observation is one of the strongest arguments supporting its existence. The cosmic web. On the largest scales, the universe is not random. It is structured like a vast network known as the cosmic web. Galaxies are not evenly distributed. Instead, they are arranged along filaments of matter that stretch across hundreds of millions of light years. These filaments intersect at dense nodes where galaxy clusters form. Between them lie enormous voids with very little matter. This structure is believed to be shaped primarily by dark matter. Ordinary matter follows the gravitational scaffolding created by dark matter, accumulating in regions where the invisible mass is densest. Over time, this process leads to the formation of galaxies, stars, and planetary systems. In this sense, the visible universe is built upon an invisible foundation. The fundamental paradox. Despite all of this evidence, a central question remains unanswered. If dark matter exists, what is it made of? Every experiment designed to detect it directly has failed so far. Every particle candidate remains hypothetical. Every theory remains incomplete. And yet, the gravitational effects are undeniable. The universe behaves as if most of its matter is invisible. This creates a paradox at the heart of modern physics, a reality that is observed indirectly with high precision, but remains inaccessible directly. Deep underground detectors. To solve a problem that cannot be seen, physicists built instruments designed to detect what should almost never happen. If dark matter exists in the form of particles, then occasionally, very rarely, it should collide with ordinary matter. But these events would be extremely faint, easily drowned out by background radiation from space, Earth, and even the detectors themselves. To eliminate interference, scientists moved their experiments underground, deep beneath mountains, mines, and rock layers kilometers thick. Detectors were constructed in environments shielded from cosmic rays. The goal was simple in principle, but extremely difficult in practice. Create a space so quiet that even a single rare interaction could be observed. These detectors often use large volumes of ultra-pure liquid xenon, or cryogenic crystals. When a particle interacts with an atom or M nucleus, it may produce a tiny flash of light or a minute electrical signal. Sensors surrounding the medium record every possible trace of energy. The entire system is designed to capture something that might occur only a few times per year, or even less. The search for a single signal. Over years of operation, these experiments have recorded vast amounts of data. Background events from known sources, radiation, neutrinos, and material impurities are carefully filtered and modeled. Occasionally, anomalies appear, tiny signals that resemble what dark matter interactions might look like. But every time, further analysis identifies conventional explanation: a stray particle, a detector artifact, a statistical fluctuation. No signal has survived full scientific verification as a true dark matter detection. The illusion of a breakthrough. At several points in recent decades, experiments have reported potential hints of detection. Some results initially appeared consistent with expected dark matter properties. For a brief period, the scientific community considered whether a breakthrough had finally occurred. But as additional data was collected, the signals faded or failed to reproduce under stricter conditions. In science, reproducibility is essential. Without it, even the most exciting result cannot be accepted. And so, each apparent discovery eventually returned to uncertainty. The universe remained silent, particle colliders, and the missing energy problem, while underground detectors wait for rare collisions. Another approach attempts to create dark matter directly. At facilities such as the Large Hadron Collider, protons are accelerated to near light speed and smashed together, producing extreme energy densities similar to those moments after the Big Bang. In these collisions, new particles can be created from energy itself. If dark matter particles can be produced in such events, they would not be directly visible in detectors. Instead, their presence would be inferred indirectly. Physicists look for what is known as missing transverse energy, a situation where the total observed energy after a collision does not match the expected energy. This missing energy could indicate particles escaping detection. However, despite extensive searches, no statistically significant evidence has confirmed the production of dark matter particles. The growing constraints. Although direct detection has failed, these experiments are far from useless. Each null result places strict limits on what dark matter can be. It cannot interact too strongly with normal matter, or it would already have been detected. It cannot be too light or too heavy within certain ranges, or its gravitational and cosmological effects would not match observations. In this way, the absence of detection has gradually narrowed the possibilities. The nature of dark matter, if it exists as a particle, must lie in a very specific and constrained region of physics, the possibility of something deeper. As experimental results continue to come up empty, some physicists began to consider more radical interpretation. Perhaps dark matter is not a single particle. Perhaps it is an entire hidden sector of physics, interacting with the visible universe only through gravity. In this scenario, dark matter would not be a single entity, but a collection of particles and forces that are completely invisible to electromagnetic observation. Another possibility is that our understanding of gravity itself is incomplete at galactic and cosmological scales. But while modified gravity theories can explain some observations, they struggle to reproduce the full range of evidence, especially at cluster and cosmic background scale. The universe without answers. Despite decades of research, dark matter remains one of the most important unsolved problems in physics. It is not a minor gap in knowledge. It is a fundamental absence in our understanding of reality. The universe behaves as if most of its structure is built on something invisible, and yet every attempt to directly observe it has failed. This tension between overwhelming indirect evidence and complete direct silence defines modern cosmology. We can measure its gravity, we can map its influence, we can simulate its effects, but we cannot yet see it, the early universe and the invisible structure. To understand dark matter, scientists do not only study the present universe, they also look back in time billions of years into the past, using the oldest light that exists. This light is known as the cosmic microwave background. It is the faint afterglow of the Big Bang, released when the universe was still young, hot, and nearly uniform. At that time, matter had not yet formed stars or galaxies. The universe was filled mostly with plasma and radiation, expanding and cooling. Small fluctuations in density existed. Even then, tiny variations in how matter was distributed. These fluctuations are extremely important because they became the seeds of all future cosmic structure. The problem of structure formation. If only ordinary matter existed, these early fluctuations would not evolve quickly enough to form galaxies. In the time we observe today, the universe would expand too smoothly. Matter would not clump efficiently. Gravity alone, acting on visible matter, would not be sufficient to build the complex structures seen across billions of light years. This creates a fundamental problem. Galaxies exist, galaxy clusters exist, large-scale cosmic filaments exist, and they all formed relatively early in cosmic history. Something must have accelerated structure formation. Something invisible. The role of dark matter in early cosmos. When dark matter is included in cosmological models, the problem is resolved. Dark matter does not interact with radiation in the early universe. This meant it could begin collapsing under gravity much earlier than ordinary matter, while normal matter was still tightly coupled to radiation and unable to form stable structures. Dark matter was already clumping into dense regions. These regions acted as gravitational wells. Once the universe cooled enough for ordinary matter to decouple from radiation, it fell into these existing wells. In this way, dark matter provided the scaffolding upon which all visible structures form. Without it, the timeline of galaxy formation does not match observations. Evidence from the cosmic microwave background. The cosmic microwave background also contains subtle patterns that strongly support the existence of dark matter. Tiny temperature fluctuations across the sky correspond to density variations in the early universe. When analyzed in detail, these fluctuations match predictions only if dark matter is included in the model. The acoustic peaks observed in the CMB power spectrum provide one of the most precise measurements in cosmology. These patterns are not arbitrary. They encode the physical composition of the early universe, and they consistently indicate that a large fraction of matter did not interact with light. The universe as a cosmic simulation. Modern cosmology uses large-scale numerical simulations to reconstruct the evolution of the universe from its earliest moments to the present day. These simulations begin with initial conditions derived from the cosmic microwave background and apply known physical laws to evolve matter over billions of years. When only ordinary matter is included, the result does not resemble the observed universe. Structures form too slowly and in incorrect patterns. But when dark matter is included, the simulation produces a cosmic web that closely matches observations from telescopes. Filaments, voids, and galaxy clusters emerge naturally. This agreement between simulation and observation is one of the strongest pieces of evidence supporting the existence of dark matter, the limit of current knowledge. Despite this success at large scale, the fundamental nature of dark matter remains unknown. It is not described by the standard model of particle physics. It has never been directly detected in laboratory conditions. It does not emit, absorb, or reflect light, and yet its gravitational influence is consistently observed across the universe. This creates a unique situation in science, a component of reality that is measured indirectly with high precision, but whose physical identity remains completely unresolved. The final question, at the center of all research, lies a single question. What is dark matter? Is it a new type of particle waiting to be discovered in high-energy experiments? Is it a hidden sector of physics that interacts with our universe only through gravity? Or is it a sign that our understanding of gravity itself is incomplete at cosmic scales? At present, no definitive answer exists. Only constraints, only models, only increasingly precise measurements of something that cannot yet be seen. End of current segment. The universe, as it appears today, is only partially visible. The rest is inferred, calculated, and reconstructed from its gravitational effects. And until a direct detection or a new theory emerges, dark matter remains one of the deepest open problems in modern physics. The future of the search. Modern physics stands at a strange point in its history. On one side, the evidence for dark matter is overwhelming at cosmic scales. On the other side, every attempt to detect it directly in a laboratory has failed. This tension has pushed the scientific community toward more advanced and sensitive experiments than ever before. Next-generation underground detectors are being designed with larger volumes of ultra-pure materials and dramatically improved noise suppression. These experiments aim to increase the probability of capturing even a single rare interaction event. At the same time, space-based observatories and large-scale sky surveys are mapping the distribution of galaxies with unprecedented precision, hoping to detect subtle deviations that could reveal more about dark matter's properties. The possibility of a new physics era. Some physicists believe that dark matter is not just a missing piece of the standard model, but evidence that the model itself is incomplete at a fundamental level. If dark matter is composed of particles, those particles would represent physics beyond everything currently confirmed in laboratory conditions. If it is not particles, then gravity itself may require revision on cosmic scales, or an entirely new framework may be needed to describe the relationship between mass, space, and time. Either possibility would represent a major shift in our understanding of the universe, the limit of human observation. One of the most profound aspects of the dark matter problem is not just its invisibility, but its inaccessibility. Human knowledge is built on observation. We measure light, energy, and interaction. We build theories from what can be detected. Dark matter challenges this foundation. It does not interact with light. It does not reveal itself directly. It does not leave behind clear traces in controlled environments. It only reveals itself through gravity, the weakest of the fundamental forces, yet the one that governs the largest structures in the universe. A universe shaped by the invisible, across billions of years. Dark matter has played a silent but essential role in shaping everything we observe today. It guided the formation of galaxies. It structured the cosmic web. It influenced how matter clumped and evolved after the Big Bang. Without it, the universe would look radically different, perhaps even unrecognizable. And yet, it remains unseen, the last remaining mystery. In science, mysteries are usually temporary. They are solved, explained, and integrated into existing knowledge. Dark matter has resisted this process for nearly a century. Each new discovery refines the constraints, but does not reveal its identity. Each experiment reduces uncertainty, but does not produce confirmation. And so the question remains open, not because of a lack of effort, but because of the limits of current understanding. Final statement: the universe is not fully visible. What we observe is only a fraction of what exists. The rest is hidden in a form we can measure, but not yet directly see. Dark matter is not just a hypothesis about missing mass. It is a reminder that the universe is still far from fully understood. And somewhere in the structure of space itself, in the motion of galaxies and the bending of light, its presence continues to shape reality silently, until it is directly detected or until a new theory replaces it. The story of dark matter remains one of the greatest open narratives in modern science.